Hello there and welcome to the first Origin screencast. Today I'm going to show you how easy it is to get started with the platform and how to generate a test pattern in 20 minutes. So the goal of this first demo is to generate an A to D test pattern that has a single source here, and from that single source pattern be able to generate it for two different devices. Number one, a device that we're going to call the Falcon, which has a Nexus interface, which is JTAG based, and which is going to run on the J750 tester. This pattern is also going to be able to target a different device called the Eagle. That's going to be an ARM-based device which has the ARM debug protocol via the ARM single wire debug physical protocol, and which is going to target the V93K tester. So the first thing to do is to install Origin following the instructions on the website. That's going to give you access to an Origin command, which has a subcommand called new for creating new applications. So I'm going to say Origin new and then the name of the application, which in my case is going to be A to D test, but you can call it whatever you like. So Origin is then going to go away and fetch the latest application templates from the web, and it's now going to come back and say which domain does my new application apply to. Now I can create an empty application, but actually the test engineering domain is what I want here. It's then going to ask me to pick from a range of subtemplates. Now right now there's only one, but this is going to be populated with a lot more over the coming weeks and months. So I'll take option 0, which is a standalone test engineering application. What I want to call it, I'll just take the defaults here based on my workspace name. And it's then going to ask me what top level devices does my application contain. So as per the initial description, this is going to have one called Falcon and one called Eagle. And now it's asking me what does the sort of hierarchy of that device look like? What sub-blocks do they have? Now you don't have to worry too much about this. You can always change it later. This is just to get you initially set up and to build some initial files for you. So in my case, I'm going to have an A to D instance, of course, and just to show in the demo, I'm going to say there's going to be two of them. So Origin has now created my application. So the first thing to do is to change into that directory. And then anytime you create a new application, always run the origin-v command. That, first of all, will boot up Origin within the scope of your application. And it will then configure a tool called Bundler, which is responsible for pulling in all of the dependencies of this new application. So it's gone ahead and done that there. Now, in your case, it might take a little bit longer the first time you run it, a few minutes, but then after that, subsequent applications will boot a lot quicker, like mine just did there. Okay, so Origin is now up and running within this application. It's recognized that we have an Origin application present, and the version of that is 0.1.0. Now, before we look at the files that it's built, I'm just going to quickly show you the console here. So you can say Origin I to open up an Origin interactive session. Now this new application has instantiated a device for me, and that's instantiated as DUT. Now this is an Origin convention that the current device is always called DUT. So here it is here. This one is actually the Falcon device this time. And there's also a tester instantiated as available as tester. And this is actually the J750 by default. But we'll look at how you can change that in a little while. The device model, the DUT, does have A to Ds present, so I told it to build A to Ds, so I can say DUT.A to Ds, and it should have two of them, which it does. So this DUT.A to Ds returns basically a Ruby array, each containing, well, this one contains two items, which are two objects representing each of the A to Ds. I can reference the individual A to Ds by saying A to Ds 0. So A to Ds is a Ruby array, so I can index that array, or I can say A to Ds dot first or any other method that Ruby supports natively. Origin will also build me a method called A to D 0 to talk to the first A to D and A to D 1 to talk to the second one. Okay, so we'll come back to this console in a little while. So all Origin applications have got a common file structure, and this will become very familiar to you after a while. I'm just going to focus on a couple of the main directories today. So first of all is the lib directory. This is where all of our code, our application code is going to live. And then for a test engineering application, the pattern directory is where our pattern source files will live. The environment directory is where our different environments are. Now for test engineering cases, the environment is used to instantiate the tester usually. So we've got a different environment file for each of the test platforms that we want to target. So the J750 one instantiates a J750 driver. The 93K one, for example, instantiates a 93K driver, and so on. And then the target files in the target directory are where the device under test, the DUT, gets instantiated. So the Eagle1 instantiates the Eagle, and the Falcon instantiates the Falcon. Now the thing that it's instantiating here is defined within the lib directory. So let me just clean this up a little bit. So within the lib directory, within the A2D test, so each of the applications has got a namespace. So our application's namespace is A2D_test. So within that namespace here are all of our files. So the Falcon here that's getting instantiated is defined in here. Now the Falcon here is an example of an Origin model. Now this is just a regular Ruby class, but we include this Origin top level module within it. That defines it or gives it access to the model APIs. But also by being the top level here, it gives it a special place. And what that does is that anytime we instantiate a new instance of this class, like we saw in the target file, Origin will recognize that this is the top level object within our hierarchy, and that will be automatically assigned to that DUT method that we used in the console. So I have a quick run through here of what it does. So initialize is a Ruby method. So anytime you instantiate a new instance of this class, Ruby will automatically call this method. And here we're just going to call a few additional methods to instantiate the pins, instantiate the registers, and instantiate the subblocks of this model. Now the model should be used to basically model all metadata that's intrinsic to the silicon or the hardware. So that means to define things like the pins, the registers it's got, any features that it's got, any bugs, that kind of thing. So our initial, kind of pre-built model here instantiates the pins for a JTAG interface, but obviously just edit those and change those to be, whatever you need for your device. We're not going to actually have any registers at the top level in our demo today, but if you did have, you would define them here. And then the subblocks is what we asked Origin to build originally. So it's created the subblock called A2D, and there's 2 instances of that. And then whenever it instantiates these, it's telling it that the class name that it should reference is A2D. So that's basically telling it to look at this A2D class or A2D model that we've got defined over here. And we'll go and look at that in a minute. Now, one thing that we're going to change here is just to add a base address. Now, there's a couple of ways to do that, but one easy way is just to pass in an array of base addresses. So we'll just say that the first A2D instance has got this base address, and then the second one has got this address here. So let's go and look now at our A2D model. So the A2D model lives here, and it looks essentially the same as the Falcon that we just looked at. The only difference is that it instantiates the Origin module instead of the Origin top level module, because this is not obviously the top level. Now within your runtime environment, you can only ever have one top level instantiated. If you try and instantiate any more, Origin will give you an error and say, you can't have any more than one top level. But you can have as many models as you like. So this is the model of the A2D. Now we are going to add some registers here. Now you can also have additional subblocks. So you can create, a full hierarchy here as deep as you need to go. In this example, though, we're not going to have any subblocks within our A2D, so we'll just get rid of that. But you would just use the same syntax as you saw in the Falcon example. We are, however, going to have some registers here. Okay, so this is a reference manual for an A2D that I'm going to be modeling here. I'm not going to model all the registers, but one of the ones I'm going to do is the A2D status and control register, which is defined like this. Key things I want to get is the offset, the register address offset, which is 0, and then I'm going to model each of these bits here. So if we go back to our model, the API to define a register is this. So first of all, we say the name of it. So this is going to be SC1 was the name, status and control 1. The address was 0, the size is 32. Now bit number 7 was called conversion complete, and the access for that was read only. So I'll record that here in the model. And then we had a register. Then we had a bit at position 6, which is called AIEN. Then we had bit 5, which was a bit called diff. And then we had bits 4 to 0, which were called A2D channel. Okay, so that's how you would define that register in Origin. I'm going to add one more register, which is further down in the reference manual here, which is the, the A2D result register, which is where my conversion will be returned. So the offset of that is hex 10, and the register is called R, result register. So let's just create that register there. So just call it R. The address was hex 10. Size 32 is fine. Now the result was in bits 15 to 0. So we'll just say bits 15 to 0. And I just called those bits D. Okay, so that's my model essentially complete at this point. I've added the registers that I'm going to care about in my pattern. Let's go and have a look in the console now to see what we can do with that. Okay, so back at the command line, I can now re-enter the Origen console, which is Origen I for Origen Interactive. Remember, I've got my .a to d's here. And if we say .a to d 0.regs, we can now see that it's got those two registers that I defined, SC1 and register R. We can now drill down to them, so I can say .a to d 0.sc1, and I get a nice graphical representation here of my register. There's the address. Now the base address has been applied based on the device that the A to D is instantiated in now. And if we look at the A to D1 register, for example, we'll see that it's picked up the alternative base address there because it's the we're looking at the second instance now. Now this register object here will behave very similar to how the register would on silicon. I can drill down to individual bits here, A to D channel bits, and then write them to a specific value. So we see now that the channel has been written to 5. I've got two A to D instances here, so that means I've got two completely independent register models. So A to D1, its register is still at its reset state there. I can obviously write that to a different value, and that holds that value there. We can reset the register, so I can say A to D1.sc1.reset, reset that individual register. Or I can in fact reset the whole device, and that will update all the registers back to their initial state. So we can see that this one's back here, like that. So that's the register model available now. So how do we actually use that now to generate a test pattern? Okay, so our demo pattern here is going to perform an A to D conversion on a given tester channel and then capture the result. So if we wanted to do that, it might be tempting first of all. So let's create our pattern. So we'll do that in the pattern directory. So we'll call this pattern A to D 0 convert on channel 10. So if we open up that file, so the way to create a pattern in Origen is just like this, and then we enter our pattern logic in here. Now initially it might be tempting to do the same as we did in the console there and say .a to d 0, .sc1, and so on. But that's really not the Origen way of doing things. By doing that, you're coupling this pattern very tightly to the current A to D implementation. If the way to do a conversion, for example, was to change, then we would have to update this pattern and any derivative patterns if you came along and copied this to make a pattern for channel 11 and so on. So we don't really want to do that. And as a general rule, you don't really want to be reaching into an object and manipulating its registers. That kind of creates patterns and environments that are hard to maintain. It's much better then to instead create an API within the model or have the model expose an API for you to be able to do operations with it. So what does that actually mean? What that means is instead of calling A to D 0.sc1, we're going to call an API method, and let's call it convert, and then let's just pass in the channel. And that's us basically done now with our pattern. We've kind of expressed what we want our pattern to do at a high level, and we'll leave the detail implementation to the model layer. So we're done here with the pattern for now. Now, one way to proceed here would be to start creating the methods that we need in here within the model itself. And initially, that's how we did build Origen applications. But the problem with that is that really this the data that's in the model here is not really owned by test engineering. This is really stuff that's owned by design. And we want to actually keep that separate from our test IP. One of the benefits of that is that it means that in the future, we could actually remove this model altogether from this application and get it from somewhere else. If it was, for example, automatically generated from design output tools or something, we could get rid of the model altogether. So we want to actually keep our test IP separate. And the place to put that then is in the controller for the given model. So Origin has built us here an A to D controller. So if we open that up here, this is the place now to put methods that actually use the given model. So we want to create our method called convert, and it takes one argument called the channel. Now the first thing that we'll do here is give a nice message to the pattern. So we'll just say performing an A to D conversion on channel, and then we'll put out the channel number. Okay, so to perform the conversion itself, what we're going to do is first of all write the A to D channel number. So we don't have to drill down here through the global namespace because we are in the controller for the A to D. So we can just say sc1 dot A to D channel dot write that to the requested channel. And let's just say that that will initiate the conversion. Now, this write method here will update the model, but that won't actually invoke any pattern behavior. To make it actually do it in the pattern, the command is write bang. So that's going to write that within the pattern. We're then going to, let's say we have to wait for the conversion to complete. So we can say tester.wait, and then time in microseconds, let's just say 100. And then at the end, we'll verify that the conversion is complete. So we'll say sc1 dot conversion complete bit, and we'll assert that that is high, that bit has gone high. And then finally, we want to return the result to the caller. So we'll say sc, and in fact, the r register dot d. Now within Ruby, the last thing that a method does is what is returned. So here I'm going to return basically the register r d bits, which is the result. So we'll just say that's a bit obscure based on this register name. So we'll just give ourselves a comment here. So this is return the result bits to the caller. And that's our pattern essentially complete. Now, a couple of things to note here are that as the A to D test engineer, I first of all don't care how the registers actually get written. I'm just expressing that within within my knowledge of my IP, these are the registers that I want to get written, but I don't care, how that actually happens. Similarly, I don't really care how the tester works either. I'm just expressing here the notion that I want to wait for the amount of time that I think it will take to settle, but I don't really care how that's actually implemented either. So this allows test engineers to really focus on understanding in detail the operation of their IP block that they're responsible for, but they can offload a lot of the logistics of how that actually runs in practice to other test engineers who are responsible for those other areas. So if we go now and try and run this pattern, we can see what happens. So the command to generate the pattern is origin G, G for generate, and then we can browse to the pattern. So that lives in the pattern directory, and we called it that. So if we run that pattern, we do get an error. So the error it's saying is that we've made a request to write register sc1. However, the Falcon controller doesn't know how to do this yet. You should implement a write register method like this. So really what that's saying then is that when we try and do this right, Origin is automatically sending that request to our top level to implement that. And it's looking for this method to be present here. And then so it's saying that we want to implement the logic here for how to actually do a write register. Now, you could do that by hand here, but one of the real benefits of Origin is that it is a platform and we can leverage each other's work now. So the Falcon device is going to use the Nexus protocol. So if we go to the Origin website and we go to the plugins page, a plugin does exist today for the Nexus protocol. Now this is a PowerPC debug protocol. So it says if you want to add that to your application, you add this to your gem file. So if I go to my application's gem file here, I'll just say I want to now use the Origin Nexus plugin. And then the plugin page gives me an example integration here. So I need to include this Origin Nexus module within my controller here. And then it's saying there's some example here of how to configure that. I'll just take the defaults right now. It's saying I should have a JTAG pin set up, and I already do have that. And then here's the methods that I care about here, read register and write register. So I'll paste these in here. Now what this is doing here is basically just offloading that request to the Nexus plugin driver. So whenever the A2D says write that register, the request is going to come up here. It's going to call this method pass in the register that's to be written. And here I'm just going to farm it off to the Nexus driver. So let's see if that works. So it's telling me when I try to run that I need to install this plugin. So we'll just do what it says here. We'll just run that command to install it. So it's also installed one called JTAG. So this Nexus has JTAG as a dependency, so it's automatically picked that up for me and installed that as well. I can at any time say Origin PL added, and that will show me the plugins that I currently have plugged into my application. Now some of these came with the pre-built application shell that I started with, but then here's the Nexus that I just added, and the JTAG, which was a dependency of Nexus. So now if I try and generate that pattern again, it works. So this has generated 128 vectors, and it's generated a J750 pattern. If we have a look at that now. Okay, so this is our pattern here. Now this is a J750 pattern that it's generated here. The startup method came from the controller. It came with a couple of pre-built methods that did some startup vectors and some shutdown vectors. Obviously, you would just edit that as required for your device. It's then performing the A to D conversion, spelling mistake there, but it's performing A to D conversion on channel 10. It's doing some Nexus transactions now, and that's using the JTAG protocol. I guess some point down here, yep, here's my wait for 100 microseconds for the conversion to occur. And then here's where it will be reading the conversion complete bit. And then at the end, it's going to reset the device. So that's my pattern, basically working. One thing I can do at this point is to save that off. And that means that the next time I generate that, Origin will be tracking it to see if any changes have happened since the last time I did it. And this time it's saying, no, it's exactly the same as the last time. This is very useful for regression testing, but also for during development to see how the changes that you're making are affecting the output. One edit I am going to make is, I'll make a couple of edits actually to show you how you could do a couple of things. The method that I created, the convert method, that if you remember, that returned these bits. We're not really doing anything with that right now. One thing that I could do in the pattern would be to store that. So I could say that the result is equal to that, and then I could just say result.store as an API that I can use to capture those bits. So if we go back now and generate our pattern again, we can see that Origin has picked up a difference this time. And if we have a look at what that difference is, then we can see that it's added these additional vectors at the bottom where it's basically reading out the register, and it should be, yep, it's injecting some store vectors here for the J750 to capture the data value to the tester. So that's that. So I'm happy with that change, so I can just save that pattern off. Now I can run this thing here, or I can just run Origin save changed, and that's going to save that off for next time. One other example just to show you. Now I mentioned that you could edit the startup method. Let's say in our example that to get into mode on this device we had to do a couple of raw JTAG transactions. So because we have the Nexus controller here available, we can say nexus.jtag .write, let's say write IR to 5. That's going to be an 8-bit write, and then let's just say we write some DR value 25. Like that. So that's just an example how you would do kind of raw JTAG transactions to get into test mode or something. So we generate a pattern there. Again, that's picked up the difference. We can have a look at that. So here now in our startup method, we've got these JTAG transactions that I just asked for. Otherwise, the pattern's the same. Okay, so hopefully that's within 20 minutes now the pattern is created. Now, what I want to do now is, if we remember the initial goal here was to create this single ATD test pattern and then target 2 different outputs. So we've done the first one there, which is the Falcon, which used the Nexus JTAG based on the J750. Now I want to run on the Eagle, which is going to be an ARM debug based device, which uses single wire debug, and on the 93K. So here is our Eagle device and controller. Now we're just going to follow exactly the same principles as before. Now this one is going to use ARM debug. So we'll go back to the Origen homepage and look at the plugins page. There is a plugin for ARM debug. So we'll go there. If we want to install it, we do this. So add that to our gem file. Then you would also, read the kind of integration notes here. One of the things it does say is that this plugin actually supports both JTAG and single wire debug, so I have to choose the one I want. So I do want single wire debug in this case, so I'm going to install that plugin as well, like so. And then going back to the integration notes, so I need to include ARM debug and also include the driver that I want. So I actually want the single wire debug one, which is like this. Okay, so I'm just defining here my Eagle uses these 2 protocols. And then back in the ARM debug page, there's an example of how to actually integrate that. So I'll just take that there. That gives me these. Now, a lot of these drivers will give additional methods to use specific things that they support. Obviously, be aware that if you start doing that, then you're coupling your IP to that particular protocol. So it's best to stay to generic methods like this if you can. So basically, every single Origen driver should always support read register and write register, for example. So that's that done. So we can now go and try it. So right now our target is set to, okay, so actually it's telling me that I need to install these new gems. So again, we just run that bundle install command first of all. So it's pulling in single wire debug and ARM debug. So now if I look at this, Origen T is the command to view the current target. I can see that it's currently set to a default, which is doing the Falcon. If I want to change that, it's just Origen T and then pick the one that I want. So I want the one for Eagle. Likewise, my environment right now is currently set to J750. So I'm just going to change that also to the 93K. And now if I generate that pattern, and the pattern was called that. If I generate that pattern, it's going to be targeting the Eagle and the 93K platform. Now I have got an error here, which is saying I've tried to reference pins single wire debug clock within that, but it does not exist. So the problem here is that I haven't read the integration instructions properly. If I go to single wire debug, it's requiring that I have these 2 pins defined. Now you can just do an alias and it will be happy with that, or you can define the pins. So back in my Eagle model, I can see that out of the box I just had this JTAG pin defined. So I'm going to add this protocol instead. I'll just take these ones out. Okay, so now we'll go and try that. Okay, so that still gave me an error. So I need a T clock pin. So there we go. So I need to update the integration guide actually for that plugin to make that clearer, but I've added that pin now. And then it generated the pattern. So if I have a little look at that one, so this will be functionally equivalent to the one we looked at before, the J750 version. This time though, this is a 93K pattern. and it's using a completely different protocol to actually test that A to D. But so this is using ARM debug. It's using the single wire debug, a 2-pin protocol instead of the 4-pin JTAG. But it's essentially exactly the same pattern that we had before. Finally, one other thing I'm going to show you is an example of a protocol aware output. So we could generate that same pattern again. This time we're going to target the J-Link, which is J-Link is a bench debugger that speaks JTAG. So I'm going to switch back here to the Falcon target because that's the JTAG based one. And now if I generate that, that's given me a different output now, which is a J-Link command file, which I can now take and run on the bench. This is going to speak to the Nexus via these J-Link commands. Now I could basically just take this pattern now and run it on the bench. If I wanted to verify its functionality or debug the silicon in some way, I can now run the exact same pattern that I'm running on the tester on the bench, and that's generated from exactly the same source. So hopefully that initial video gives you an idea of what you can do with Origen in terms of pattern generation. Really, in a very short space of time, I've managed to have a single source pattern, which I've managed to generate for multiple platforms and multiple devices. And that's been done by leveraging the Origen community that provided me with drivers to get me started quickly. So there'll be a lot more videos coming in due course to show more advanced concepts and additional things that you can do. In the meantime, please do get involved with the community. Come and say hello, ask questions in the forums, and we look forward to working together with you in the future. Okay, thanks a lot. Cheers now. Bye-bye.